In this session, I'm going to talk about conditional probabilities. So, wherein I'm talking about two different events A and B, right? For these two events A and B, I want to know what is the probability of occurrence of A given that B has already occurred. In a general probability scenario, I'm just trying to find out the probability of occurrence of A. So that kind of a probability is called as unconditional probability. I'm simply finding out what is the probability of occurrence of A. But in this scenario, what I'm trying to find out is, I know that the event B has already occurred. Given that this event B has already occurred, I am trying to find out, is there any kind of change in the probability of occurrence of A with this additional information given to me? With the additional information of B being occurring, if that information is given to me, is there any kind of change in the probability of occurrence of A? So that is what we generally denote it as probability of A given. Given is with a straight vertical line. Given B. Probability of A given B. So what is the probability of occurrence of A given the event B has already occurred? Right? So the typical way we find it out is the probability of A intersection B, because if you try remembering, if you try relating it, I know that the probability of B has already occurred. I don't know whether A has occurred or not. So we want to find the probability of occurrence of A, which is as good as probability of occurrence of both A and B divided by the probability of occurrence of just B. So this could be with A or without A, which means it could have been written as probability of occurrence of A intersection B divided by probability of B occurring with A or probability of B occurring without A complement intersection B, which is as good as probability of B occurring, right? Instead of this entire thing, I could have simply written it as probability of B occurring, because it is whether A has occurred or not. I'm finding out what is the probability that B has occurred. Then given B has occurred, what is the probability that A also has occurred? Both A and B have occurred divided by the probability of B occurring. That is an interesting relationship or a formula which is called as a conditional probability formula. Probability of A given B is nothing but probability of A intersection B divided by probability of B. We are going to use this formula a many number of times. And one more derivation from this. From this, if I am more interested in finding out probability of A intersection B, it is nothing but probability of B multiplied by probability of A given B. Means A intersection B is nothing but one of the events occurring, and given that the first event has occurred, what is the probability of the second event? So I could have very well written this as probability of A multiplied by the probability of occurrence of B given A. Either ways I can write probability of A intersection B. So one important corollary that is coming out from this, which is otherwise called as the multiplication rule of probability. Probability of joint occurrence of A and B is what we have computed. Probability of A multiplied by probability of B given A, or probability of B multiplied by probability of A given B. Now, in this context, let me introduce you to the world of independent events. What are independent events? Those events, let's say if the event we are talking about the event B occurring, assuming event B has occurred, we want to find out probability of event A occurring. That is what is P of A given B, whether B has occurred or not. Think of it like this. Whether B has occurred or not, if my probability of A is the same, for example, I have thrown the dice first time. I got an information of 3. I got a value of 3 on the dice. That is the event A. Now, given that the first throw of the dice is a 3, I want to find out the probability of second throw. How does it matter? How does it really matter whether I get a 3 on the first throw or a 5 on the first throw? The second throw is completely independent of the first. So, the probability of B occurring there has no relevance for the occurrence of A. In that case, we call A and B are independent events. So in that case, probability of A given B has no relevance to the probability of occurrence of B. In those cases, it simply becomes probability of A itself. There is no change to the occurrence of the probability of A because of additional information given that the event B has occurred. So probability of A given B will be same as probability of A itself if the events A and B are independent. Because there is no additional use that I am getting whether the event B has occurred or not. Right? So even when we are talking about probability, so from here if I am trying to find out the probability of A given B, now it is becoming probability of A itself. So which means probability of A is nothing but probability of A intersection B divided by probability of B, which in other terms is becoming probability of A intersection B is simply becoming the multiplication of the two probabilities. If the events are independent, if A and B are independent events, see that this is where some of the rules you have to be comfortable with. If the events A and B are independent, the probability of the intersection between the events is same as the multiplication of the individual probabilities. These are not mutually exclusive events. These are independent events. In case of mutually exclusive events, their union was a summation of the individual probabilities. In case of independent events, the probability of their intersection is the simple product of their individual probabilities. So some of the important points that we really need to understand in this context. Then the next point that would be of use in this context is the concept of total probability. It's a very interesting concept. Let's think about the total sample space. This is the total sample space. I divide it into n parts, equal, unequal, whatever it is. I divide it into n parts, right? But these n parts are mutually exclusive, right? These are n parts which are mutually exclusive events for me. So the different events for me are E1, E2, so on, En. Because they are mutually exclusive, the intersection between any of the pairs, E1 intersection E2, is always a null set, right? E1 intersection En is a null set. So any kind of between any pair, between any event, the intersection is null set, and their union, all of them put together, is equal to the sample space. Because we have taken the sample space, broken the sample space into n mutually exclusive events. Now, let me bring in some additional event A. Let me bring in some additional event A, which is a subset of some S. The same subset of S. I am bringing in some external event A. Now, the point is I can very well write A as a combination of all these things. I could have written A as A intersection E1 union A intersection E2, so on A intersection En. This is a very interesting relation. A as such, I can very well express it as how much it is intersected with E1 union, how much it is intersected with E2, how much intersected with En, because E1 to En is the whole sample space. So it's as good as, think of it like this. I have broken it down, right? Let's take an example where it becomes simple. The sample space is 1, 2, 3, 4, 5, 6. And I have broken it into three pieces. 1 and 2 is one piece, right? Calling it E1. 3 and 4 is another event. 5 and 6 is another event, E3. Now I have an event A, which is 1 and 5. So this A, I could very well write as A intersection E1. What is A intersection E1? The intersection between these two is just 1. Union A intersection E2. A intersection E2, no commonality between A and E2, so it is 5. A intersection E3, 1, 5, 5, 6, so it's 5. The union between these three is nothing but 1, 5. So which means A can very well be written as A intersection of each of these events, provided, what are the rules? These events E1, E2, E3, they should be mutually exclusive and their union should be the total sample space. So A can very well be written in this form, which means now I'll apply the probability also in this form. P of A, I'll write it as, because one, they are mutually exclusive. If they are mutually exclusive, the probabilities are the summation, a simple summation. So it will become probability of A intersection E1 plus probability of A intersection E2 plus so on probability of A intersection En. This is a very interesting relationship. Probability of A you can very well write it as probability of A intersection E1 plus probability of A intersection E2 plus so on probability of A intersection En. This is what we call as the law of total probability. So the occurrence of any event, the probability of occurrence of any event A belonging to a sample space S can very well be written as the probability of occurrence of A along with another event E1 along with another event E2, where E1, E2 and so on form n different mutually exclusive events out of the subset S. That is a very interesting conclusion or a theorem that is coming out, which is called as the law of total probability. And this concept of law of total probability forms one of the interesting inputs to what we call as a Bayes theorem, which is very heavily used in the world of statistical inference. Bayesian way of statistical inference is something which we keep seeing as some of the interesting aspects in the world of statistics. Now, a few important or what is the Bayes theorem all about? Some of the things that the Bayes theorem is based on is finding out the probability of occurrence of an event given A. Right? Let's try to express this. Now we know we'll go with E1, E2, En. They are mutually exclusive partitions of the subset S. And I am having an event A which is a subset of S. Now we know that the probability of any event I occurring, event E1 occurring given A is nothing but the probability of E1, let me take one, E1 intersection A divided by the probability of A. Are we fine with this? Now, probability of E1 intersection A divided by probability of A. Now, I will write probability of A using the total probability rule, which is probability of A intersection E1 plus probability of A intersection E2 plus so on probability of A intersection En. That I can very well write. And now each of these intersections is nothing but probability of E1 multiplied by probability of A given E1. This is what is the multiplication rule, plus probability of E2 multiplied by probability of A given E2 plus so on. So the denominator P of A is nothing but the summation of probability of EI occurring multiplied by probability of A given EI. That is the denominator. Now what about the numerator? Probability of EI intersection A. This I'll write it as probability of A or probability of EI multiplied by probability of A given EI. Now if you look at this, I can very well write, if you take these two parts, I can very well write probability of EI given A as probability of EI multiplied by probability of A given EI divided by the summation of probability of Ei's multiplied by probability of A given E's. This is what for all the I's, I'll sum them, multiply it and sum it up. And this is what we are simply calling as the Bayes theorem. So the simple way of looking at it is I can very well find out the probability of EI occurring given an event A has occurred by considering probability of A given EI, which means I am simply finding out the turnaround probabilities, turnaround conditional probability. By knowing probability of A given EI, I am able to find out probability of EI given A. So I am able to find out turnaround probabilities. So if you look at it, okay, probability of EI, initial probability of occurrence of EI, which is called as priori probability. So initially the probability of occurrence of EI is this much. Now a new event A has occurred. Because the new event A has occurred, I am thinking that the probability of EI could change. So this is like an updated probability of EI given A has occurred. That is the reason we call this as posterior probability. The probability after the occurrence of the event A. This is the probability before the occurrence of event A, and the first one is the probability after the occurrence of event A. That's where we are calling it as the posterior probability. And we know that the event A has occurred. So so if I have to find out the posterior probability, we have to know what is the probability of A occurring given E1 has already occurred or EI has already occurred. And the denominator, I'm looking at the probability of A occurring. And if the probability of A occurring is what I'm looking at, it is nothing but the total probability, law of total probability being used. In short, if you have to remember it, it's like this. Probability of EI given A is nothing but you start with probability of EI, multiply it with probability of A given EI, divide by probability of E. So this probability of A, you are expressing it as the law of total probability rule. Or in other terms, if you have to give a simplicity altogether, P of A intersection B. We have already discussed it as P of A times P of B given A. The same thing I can write it as P of B times P of A given B. Because both of them are the same, equate it. P of A multiplied by P of B given A is same as P of B multiplied by P of A given B. Now just use one of them. P of B given A is nothing but P of B multiplied by P of A given B divided by P of A. This is what is the Bayes theorem. So this is the priori probability, the probability of B occurring initially. Now I am looking at any updating to the event B given A has occurred. So this is the posterior probability. This is the priori probability. And now the event A has occurred. So what is the probability of occurrence of event A is there in the denominator. Probability of occurrence of A given B. All this put together is going to give me the updated probability of occurrence of B given A, which is called as the posterior probability. We have lots of applications associated with this Bayes theorem. So we really need to be slightly comfortable with the usage of this Bayes theorem and what is it all about. When we take a couple of numericals, things become more and more simpler for you. All right. So thanks a lot for listening to this session on conditional probabilities. Thank you very much.